Welcome folks. So in this video I want to show you another way to calculate the dot product, and this is the way that you'll see in a lot of textbooks and in the book that we use anyway. It starts off by giving you this formula with no context. It just tells you just how you do it. In this video I hope to make sense of why that property, or prove to you why that formula is what it is. Okay, so once again, pretend we have two vectors, and I'll just call this vector A. These are two-dimensional vectors. Technically, you can actually calculate the dot product with any dimensional vectors as long as they're the same. So you could have a three-dimensional vector dotted with a three-dimensional vector, a 24-dimensional vector dotted with another 24-dimensional vector, and so on. The geometric meaning, again, would be slightly lost, probably, at least on me, but it'll calculate the same. Let's just remind ourselves, again, that the dot product, so I'll say A dot B, again, a vector times a vector, again, specifically vector dot a vector, is equal to the magnitude of A times the magnitude of B times the cosine of whatever the angle is between them. Okay, here's what I'm actually going to do. It's going to look kind of crazy, but remember, I'm not trying to necessarily prove anything right now. I'm just trying to show you that this can actually be calculated. The value of this, again, this is just some number. This is a scalar, a number. You can actually get this number without actually finding out the magnitude or about the angle. Because we have a slight problem here, is that you couldn't calculate this value of this dot product. And we'll see examples later about why you would want to calculate the dot product. You can actually calculate this dot product, this value, without even knowing the angle. Okay? Because if you wanted to use this formula, you would need the angle. Okay, so enough about that. What I'm going to do is I'm going to create a triangle based off what we have here, and I'm going to connect these two heads of these vectors. Okay, so I'm just going to draw a little blue vector right here. Okay, so let's clean this up a little. That'll go right there. That will go right there. Okay, what is this vector? Well, I'll call it vector C. But again, what we're trying to do is I want to be able to calculate the dot product without any other information other than what A and B are. Here's how I could do it. Well, notice that the green vector B is actually just A plus C. If I start off right here, I follow the path of A, and then to C, I end up with B. So that means that A plus C is equal to B. Let me clean that up. Vector A plus C is equal to vector B. And if I rewrite this, this simply means that vector C is equal to actually B minus A. That's really handy because we can actually figure out the components of vector C then. Would simply be, the first component would be, well, again, subtract the corresponding components from in B and A. So I have B1 minus B2, A1, B1 minus A1, and then B2 minus A2. Hold off on that, okay? Here's my question, is how could we calculate the magnitude of, how can we connect the length of all three of these sides? Now, this is not a right triangle, unfortunately, so we can't use the Pythagorean theorem. However, it is a triangle, and we actually have such a tool that connects the sides of any triangle, and that is the law of cosines. Again, provided we have an angle. Okay. Now, again, I said before, we're going to not need the angle at the end of the day. So just hang on, just bear with me here, but we will require this angle for the moment, just for this formula. So let me remind you what the law of cosines says. The law of cosines says, well, if I have two, let's pretend I have some random triangle, because it has been a while, and I know two of the side lengths and the angle between them, and I'm trying to find, say, the third side length, which is, again, opposite the angle. This would say that C squared is equal to A squared plus B squared, so it's very similar to the Pythagorean theorem, but then you subtract 2AB cosine of the angle. Okay. Notice that when this theta is a right angle, then cosine of 90 degrees is 0, and so that's why this is the Pythagorean theorem. So the Pythagorean theorem really is just a specialized version of this, or specific version of this. So let's apply this to our scenario. Now again, the side lengths are really the lengths of the vectors or the magnitudes of them. The length of the arrows, I guess you could say. Okay, so really what we have is so C would be this side. So the magnitude of C is really the magnitude of B minus A squared is equal to, let's see, A squared. So it's not actually A, it's the magnitude of A squared plus the magnitude of B squared minus 2 times, instead of just A times B, it's the magnitude of A times the magnitude of B cosine of the angle. Okay, you might have found something here. Notice that already this right here is the dot product. So I'm actually just going to replace that with that right now. Okay, so instead of that, I'm just going to write down right here. Let's do it gently like so. This is just negative 2 times A dot B. Alrighty. Okay, so what we're going to do now is we're actually going to, it's going to look a little messy, but we're going to expand these magnitudes. Remember that, and I'm just going to do this once, the magnitude of, say, B, the magnitude of vector B is going to be equal to, again, Pythagorean theorem essentially. So this is the first component squared, B1 squared plus B2 squared, and then you take the square root of that whole thing. But in this law of cosines formula, we don't actually care about the magnitude, we care about the magnitude squared. And so the magnitude of B squared is going to simply be B1 squared plus B2 squared. Okay, so I'm going to expand this then, like so. So this vector B right here is, we know that is going to be B1 squared plus B2 squared. If I was going to be really, really fancy schmancy, I would color code this whole thing, but in the interest of time, I think I will not. This video is already running a little long. A squared then, sorry, the magnitude of A squared will be similarly A1 squared plus A2 squared. And then on the right side, we'll finish up with minus 2 A dot B. And then we'll start off with this. So this is going to be kind of messy, but just be careful. So again, the first component of it is B1 minus A1. Again, we're looking at this one right here. So that's just going to be B1 minus A1 squared plus, well, the second component squared, B2 minus A2 squared. So again, all I've done is I just written out the magnitudes and expanded them. Normally, again, these would have square roots over them, but since they're being squared, those square roots just go away now. Okay, looks a little messy, and it's going to get, bear with me here, it's going to get a little bit messier. I want to expand these two binomials. And what do I get? Well, B1 minus A1 squared, that's going to be B1 squared minus 2 B1A1, but I'll write it like so. A1 B1, just keep it in alphabetical order, plus A1 squared. Okay, if I work with this one now, that's going to be B2 squared minus 2 A2 B2 plus A2 squared. And then the rest follows, so I'm just going to grab this and copy paste it. Oopsies. So let's scooch over here. Okay, hopefully you're still with me. Again, this was the hard part, was maybe noticing this part and then remembering the law of cosines, okay? But once we got it down to here, hopefully you can see that we're just expanding these components here. Alrighty. Whew. But now we can actually notice that we can actually cancel some things out and simplify this. Remember, we're trying to get an equation for this, or an expression for that. So we want to get rid of as much as we can. Notice, I have a B1 squared here and a B1 squared here. I have a A1 squared right here and an A1 squared right there. So cancel those. I got a b2 squared, and an a2 squared, a2 squared. So what's left over? Well, the only things that are left over are this, that, and that. So what I'm going to do is I'm going to collect my like terms on the left side and factor out that -2. So I'm going to end up with -2 a1b1 plus a2b2. On the right side, you can see it now, I hope, 2 times a dot b. We can divide both sides by -2. That, and we end up with this really just beautifully simple formula where I'm going to flip the order here. I'm just going to flip the sides here and say that a dot b, again, remember that vector a is equal to a1, a1 comma a2. That's really ugly. a1 comma a2, and b, vector b, is equal to b1 comma b2. Notice that to get their dot product, the actual value of it, all you have to do is take their first components, multiply them together, then add to that the product of their second components. Oops, a2, b2. I just think that this is kind of beautiful, which is kind of crazy if you think about it, because again, what is the dot product? Well, it tells you, again, if we talk about referencing our last video, it tells us how much one vector, quote unquote, how much does one vector point in the same direction as the other one? How much do they kind of, quote unquote, contribute to each other, if you want to think of it like that? Now, normally you would think, okay, well, I would have to know how much this angle is, because of course, if the bigger this angle is, the less it contributes. Right? Keeping the vector or the length. Sorry, keep maintaining its length. If this angle opens up more, then it points less in the direction of the green one. And yet we can actually just figure that out without actually knowing what the angle is, as long as we know the components of each one. Now, of course, yes, the components will affect what that angle is, so that's why this works. But I just think that it's just so beautiful and simple. I don't know how else to explain it. So I'm sure that wasn't fun necessarily for a lot of you to listen to work through, but I hope now at the end of it you can see and appreciate, well, if I want to calculate the dot product of these two vectors, I can actually just do this, which is just a super fast calculation. Alrighty, and this actually might be the way you thought to multiply vectors in the first place. Like if I just gave you two vectors and said multiply them without any context of like knowing what vectors, how to actually multiply vectors, I think it's totally possible that, you know, a handful of you might have done it just because it feels right, not for any particular reason other than that. Right? So I just think that's super duper cool. And so I hope some of you do as well. Alrighty. Thanks for watching, and, you know, stay spicy, folks.